Let's talk about the pH scale. Now, the pH scale is actually measuring how acidic or how basic a solution is or an environment is. And what we're actually measuring is the concentration of a hydrogen ion. Concentration of hydrogen ions. So I'm going to put a little H plus here to represent our hydrogen ions. And so when we think about the term pH scale, I've heard it referred to as the potential for hydrogen. And that's what the P and the H actually stand for. I've also heard it referred to the power of hydrogen. Really what we're measuring are those hydrogen ions. And so in the concentration of hydrogen ions, we'll be able to tell how healthy an ecosystem is for the particular organisms that are living there. Now, when we talk about concentration of hydrogen ions, we can use a little shortcut here. We can use these angled brackets around our H plus, and then this you would read here as hydrogen ion concentration. So we're reading this as hydrogen ion concentration. Okay. Let's take a look at the basic scale. We go from 0 to 14, with 7 being neutral and right in the middle. And everything south of 7 is referred to as an acidic solution or as an acid. And so we know that your stomach acid has a really low pH, a car battery acid is a low pH, things like lemon juice and grapefruit juice, even tomatoes, soda, Coke and Pepsi, those have a low pH as well, so a little hard on your teeth. Acid rain, which we'll talk about, has been measured lower than pH of 4, but this is pretty low when you compare it with normal rainwater pH, which is just barely acidic, a little bit below 6. And that's normal. And we'll talk a little bit more later on about why that is. This basically has to do with combining water with carbon dioxide in the atmosphere, producing a weak acid known as carbonic acid. So those are our acids. And if we look at the other end of the scale, everything kind of north of 7, these are referred to as basic solutions, or we can use the term alkaline. Either one works. So seawater is naturally a little bit basic. Cleaning supplies like ammonia, oven cleaner is going to be way up here, drain cleaner, bleach. I don't think I've got these here at the exact right pH values, but they're all kind of clustered up here at the far north end of the pH scale. And those are all really damaging to cells, really damaging to living organisms. So when we're measuring pH, we're measuring something concrete and quantitative, namely the concentration of hydrogen ions in a solution. So where do those hydrogen ions come from? Because we don't see them floating around all the time. Well, they can come from chemicals. They can come from pollutants, of course, things discharged into waterways, into rivers and lakes and streams. And Mother Nature contributes her own as well. So let's talk about that. Water, good old H2O, likes to break apart from itself or dissociate. And this happens normally and naturally and kind of all the time. So when a water molecule dissociates, it dissociates into two ions, namely a hydrogen ion, a positive cation, and a negatively charged OH or hydroxide ion. Now, when those two ions are in equal concentration, that is the same amount of each in our solution, we have something in the neutral range. So if we have hydrogen ion concentration, using my shortcut, is equal to the hydroxide ion concentration, we have a neutral solution and a pH of 7. So there's no difference in either concentration. If there's a difference, then we either have a base or we have an acid. So down here in the acidic range, if my hydrogen ion concentration is greater than my hydroxide ion concentration, then I have a solution that's an acid. Now it can be a weak acid way up here, or it could be a very strong acid down below. Right, so there's sort of a range of acidity. If my hydrogen ion concentration is less than my hydroxide ion concentration, then I have a base. And I can also have, in the same way, I can have a weak base or a strong base. So really we're looking at the relationship between these two ions, and we're actively measuring the concentration of hydrogen ions in our solution. And so some pollutants can act as acids in the way that they donate or they put out into the environment extra H pluses. And so we end up with a lot of these hydrogen ions in our acidic solutions. Okay. One final thing to note about the pH scale is that it is not linear. As a scale, it is not linear. And by that I mean a pH of 8 is not twice as basic as a pH of 4. And the scale is actually a logarithmic scale. Kind of like the Richter scale is a logarithmic scale. Familiar with that? The Richter scale is what measures the magnitude of earthquakes. And so any small change in earthquake magnitude is really reflected in an enormous shift in the amount of energy that's released by that earthquake, right? So you can have a tiny change in the Richter scale value and a huge difference in the strength of the earthquake. So this is a logarithmic scale as well. And what that means is that each time I move from one number in my scale to another number in my scale, it's a 10-fold difference in hydrogen ion concentration. So a solution with a pH of 9 is 10 times more acidic than a solution with a pH of 10. A solution with a pH of 5 is 10 times more basic than a solution with a pH of 4. And these are cumulative changes. So if I have a solution with a pH of 4, and I want to compare that to a solution with a pH of 6, 10 times here, 10 times there. My solution with a pH of 4 is 100 times more acidic than a pH of 6, so 10 times 10. If I have a neutral solution at 7, and I pollute my environment with acid rain and chemicals from a coal-fired power plant, now my new pH is 10, 100, 1,000 times more acidic. Maybe 10,000 times more acidic. Who knows? Okay, so there's your pH scale and your hydrogen ion concentration.